section 1-2, mathematical models. You're going to find that this is even more review of Algebra 2 and pre-calc. You might need your calculators for this. That would be a good idea to have out. All right. So within calculus, we're going to do a lot of, and I said this last section too, we're going to do a lot of trying to figure out what type of equation works best and try to analyze the ins and outs of that equation and say, okay, if this is the equation that we think is going to fit, how do we test that? And once we test that, if it does not fit very well, what do we do with that? Okay. A mathematical model is a mathematical description, often by means of function or an equation, of a real-world problem, real-world phenomena such as the size of population, demand for a product, speed of a falling object, concentration of a solution, product in a chemical reaction, the life expectancy of a person, cost of emission reductions, all those different things. We can model pretty much any scenario using some sort of mathematical equation. The purpose of the model is to understand the phenomenon and to perhaps make predictions about the future. It's so funny. I'm the nerd kind of guy that when this whole pandemic started and everything, I was like watching all of the graphs, and I've been watching all of the graphs for like forever. I think this mathematically, this is really the best thing to say. I think this situation is so interesting. I think it's so cool to see how the graphs ebb and flow and like when peaks happen and when they don't. And, I just think this is really interesting. And so I've been looking at this current surge that we're having and seeing like, okay, if this happens the same way that our big surge happened way back in Christmas time last year, it started this time, it ended this time, when would it end? And try to see, okay, can we make predictions about the future? Like I was thinking to myself, so the surge started happening, the big Christmas surge that happened over the past year, started in October, at the very beginning of October, and by the end of February, it was done. We were at the bottom end of it, right? So if that happens again, which hopefully it doesn't happen as big as last time, and will happen as long as last time, by Christmas time, this surge will be over. If it follows the same pattern. But again, if it follows the same pattern, that's like, if, I don't know. If is a big word there, right? But what am I doing there? I'm trying to mathematically reason through what's happening now to make predictions about the future. And we'll do that, pretty much the entire course. We'll try to make, we'll figure out a problem. We'll try to make a mathematical model that fits that situation, whether that means by data, whether that means by maybe I'm given coordinates and I'm asked to find a graph that goes along with that coordinates. We're going to learn a lot more about like derivatives and integrals and say like, okay, how does that fit into the equation? And then we're trying to make conclusions based off that to predict what might happen in the future. Sometimes, got to go back to the beginning and figure that out again. Maybe we did something wrong or a mathematical model doesn't fit, right? You guys, those of you in statistics, I mean, that's what you do in statistics all the time. Figure out what works, see if it doesn't work, and then maybe you have to go back to the beginning again. Okay, so basically today is all the different types of, this section is all the different types of models that we could have. Man, we could have all sorts of models. We could have linear, we could have polynomial, we could have logarithmic, we could have exponential, we could have power models, all sorts of different things. And that's what we're really going to be talking about today and in this lesson. When we say that y is a linear function of x, so we're starting off with linears. When we say that y is a linear function of x, we mean that the graph of the function is a line. So that basically, as x is increasing, y is increasing at that same rate. And that rate being the slope. M is the slope of the line, B is the y-intercept. We talk about it all the time since Algebra 1. So let's take a look here. We have this given problem. As dry air moves upward, it expands and it cools, and the ground temperature is 20 degrees. At the temperature at height of 1 kilometer is 10 degrees Celsius. So we're given some data, right? We're given two pieces of data. If the ground temperature is 20 degrees Celsius and the temperature at 1 kilometer is 10 degrees Celsius, express temperature as a function of height, assuming that it's a linear model, assuming that what we're having is a linear relationship, okay? So that means, again, I want to write temperature, oops, that's an eraser. I want to write temperature as a function of height, right? Temperature is a function of height, given this information, given the fact that if we are 0 meters above the ground, we are at 20 degrees Celsius, right? Because that's what we have here. Independent variable is my height, Dependent variable is my degrees. And then at 1 kilometer above the ground, we are at 10 degrees Celsius. So we have 2 points, just like we did going over the homework right now. We got 2 points. We can make a line. Let's find the slope. So the slope is y minus y over x minus x. Oops, that's 0. That was weird. 20 minus 10, y minus y over x minus x, 0 minus 1. So this is negative 10, right? 20 minus 10 is 10, 0 minus 1 is negative 1, so 10 divided by negative 1 is 10. All right, so our slope is negative 10. What does that mean? That means that at every kilometer that we move up, we are going down 10 degrees. That's our rate of change, right? That's our rate of change. So my equation can say T of h is equal to negative 10h, but where do we start? Do I need to do that whole process of solving for b? No. I'm given my y-intercept, aren't I? So I can say T of h is equal to negative 10h plus 20. 0 comma is always our y-intercept, so work smarter, not harder. Could we have done that whole process of solving for b? Sure, but we would have resulted in the 20 anyway. So express as a function of height. Did we do that? Yes. Now, part B says, so that's part A. Part B says, draw the graph of the function in part A and determine what the slope represents. I kind of already did that. Kind of already did what the slope represents. It represents the rate of change of temperature, right? All right, so let's graph it real quick. So let's say, I'm going to have to do this because temperature is going to go into the negatives, right? So this is as h keeps moving forward. This is h, and this is T of h, right? As h keeps moving forward, as we keep getting bigger and bigger with our heights, generally what's going to happen to our temperature, it's going to keep getting lower and lower and lower and lower. All right, so where do we start? Let's make it by tens. Let's go 10, 20, 30, negative 10, negative 20, negative 30, negative 40, negative 50. And let's go 1, 2, 3, 4, 5, 6. Sure, we're not going to go out that far, but that's okay. So at height 0, we are at 20 degrees. Let's assume that we're not going to go underground. Yeah, let's assume that we're going to start at 0 height. Okay, at 1 kilometer, 10 degrees. At 2 kilometers, 0, 3, negative 10, 4, negative 20, negative 30, negative 40. And we can say, I'm going to put an arrow on the end of that line, we can say that it will keep going on. I bet at some point it's going to stop getting colder and reach a point where it's going to stabilize, but we're saying, assuming it's a linear model. We are just going strictly by the mathematics here. We're saying, okay, assuming it's a linear model, this is what's going to happen. What is that temperature at a height of 2.5 kilometers? So we're using what we know and assuming it's linear and saying, okay, predict the future. What's going to happen at 2.5 kilometers? Well, we're really going to be finding T of 2.5, right? We don't have to just use the graph because we have an equation that we're using to model. So T of 2.5 is negative 10 times 2.5 plus 20. So let's figure out what that is. Negative 10 times 2.5 plus 20. Negative 5. Temperature at 2.5 kilometers is negative 5 degrees Celsius. I mean, we've been doing that since algebra 2. Well, really kind of algebra 1 almost, all the way back to linear functions. But using that and like determining what's going to happen in the future, that might be, you know, that's really what's going to happen later. Okay. All right. Questions about that? Okay. All right. Let's keep going then. If there's no physical law or principle to help us formulate a model, we constructed what's called an empirical model. An empirical model, which is based entirely on collected data. Remember doing like linear regressions and quadratic regressions and quartic regressions and so on and so forth? That was what we now can call an empirical model. An empirical model is basically using data and saying, okay, if this set of data relates to this set of data, what type of equation can we have? An empirical model, which is based entirely on collected data. we seek a curve that fits that data in the sense that it captures the basic trend of the data points. You know, we can have all sorts. You, Mr. Blankenship?
Yep.
Welcome.
I just look anywhere.
Anywhere you want. But what we have here, I'll help you out here after I'm done with the lesson. I'm recording now. So based on this, Table 1 lists the average carbon dioxide level in the atmosphere measured in parts per million at Mauna Loa Observatory from 1980 to 2012. So we have carbon dioxide levels at Mauna Loa Observatory in Hawaii. And it's taken looks like it's once a year from 1980 to 2012. Use that data in Table 1 to find a model for the carbon dioxide level. What can we assume is happening? The carbon dioxide level, based on the data points, is increasing, right? The carbon dioxide level is increasing. So let's find a model to fit this data. Let's find a model to fit this data. Let's do that in our calculators. Throw back to Algebra 2. Oh, can you guys read that? Is that big enough for you guys? This might be a good idea for you guys to actually do in your calculators because it's been a minute since you guys have done this probably. But I'm going to show you where everything is. We're going to, again, take a linear regression for this data. So what we do here is we go into edit our lists. Go stat and hit edit. Okay. Remember that you can go up to list 1 and list 2 and clear. Don't hit delete. Please hit clear and hit the down arrow. And we can plug in our information. So I'm going to start plugging away here. 1980, 1982, 1984, 1986. Oops. Dude, I think I did 20,000. Nope, I did 2,000. I'm all right. 2002, 2004, 2006, 2008, 2010, 2012. It looks like about 18 pieces of data. Looks like it's taken every 2 years. And now we say, okay, 338.7, 344.4, 347.2, 351.5, 350, oops, shoot. Okay, 356.3, 358.6, 366.5, 2, 377.5. Sorry, I'm talking to myself. 9, 385.6, 389.9, 393.8. Okay. At least it looks like I've gotten the exact same amount of data. That's good. Looks like there's decimal points in every place, so I'm generally in the right direction here. Okay. So we've inputted our data, right? To figure out what our linear regression is, remember we go back out to our home screen. Okay, we go back out to our home screen. And then we go stat calc 4 is linear regression. Stat calc 4 is linear regression. And you run it. And here we have our equation. And that stat calc 4 is your linear regression. And I'm going to make this over here. Okay. Now, what did we do there? What is our calculator doing for us? I really hope you appreciate the amount of work that your calculator is doing for you right there. In statistics, when I took it in college, I had to do this by hand. Like, we had our calculators to kind of check ourselves, but we had to show the work by hand. What does that mean? Basically, what we're doing here is you're taking all of the x values and all of the y values and finding the differences between them and then finding the average of the distances between them. And then you're doing the x values and the y values so you can find the average slope of the line. And then once you find the average slope of the line, you got to do all of that with the y-intercepts to figure out what the average y-intercept is going to be as well. So this process that we just did in our calculator for like 2 seconds when we hit stat calc 4 would have probably taken you about 10 to 15 minutes to do by hand. So appreciate the work that the calculator is doing for you. But it's given this equation. y equals 1.7126, we'll round to 4 decimal places, x minus 3054.1467. That's our equation. That's the equation that models the carbon dioxide level from 1980 to 2012. And we're going to assume that this pattern will continue. We assume that this pattern will continue. Now, the next example that we have here says, use that linear model given in equation 2 to estimate the average CO2 level for 1987 and then to predict what's going to happen at the year 2020. According to this model, when will the CO2 level exceed 420 parts per million? So what we're doing here is what we're going to do is take that equation that we found, take that equation and then interpret our results and predict what's going to happen at different times. Okay? So we have this equation, this 1.726, this equation, and then we're going to say, okay, what's happening at 1987 and then what's happening in 2020? Now, we could use our calculators to do this, or you could just plug it in. You could plug in 1987 in for x and then plug in 2020 in for x. But we are smart, and we know how to use our calculators. To show you, just to remind you how to do this, you can actually go back and plug this stuff into your calculator. Now, those of you guys who had Mrs. Napple, I don't know if I gave you guys, I think I probably gave you guys this. Those of you guys that had Mrs. Napples or me, maybe, were given, let me see if I kept it in my modules. Oh, yeah, I had it pulled up. Oh, I didn't put it in there. Maybe I will upload this. This sheet might ring a bell. Let's go into Honors Algebra 2. Chapter, what was that? I think it was chapter 2. No. Oh, 2.7 stuff, was that it? Yeah. I'll put this in modules because this is how to do a linear regression in your calculator. Remember this sheet of paper? Yeah. I'll put this in modules, so if you want to print it out, you can. But you got this way back in Algebra 2. It's just basically a screenshot by screenshot direction on how to do everything that we're doing here today, based on linears, right? Once we move on and start doing quadratics and full polynomials, that might be a little different. But for linears right now, this is what we got. Okay. Now, so use the linear model given by equation 2 to estimate 1987. We were here in our calculators. What I want to do is plug in my statistics into my calculator. I'm going to turn on plot 1. And then I'm going to plug in my equation. Now, to plug in your equation, you got to go to VARS. Stands for variable statistics. You scroll down to statistics, section or part 5 there, and then right twice to EQ. And you can plug in your regression equation. And now I'm going to go to Zoom Stat. Zoom Stat, all the way down to Zoom 9, and it's going to plot our scatter plot as well as our line of best fit. Now, what is that helping? Well, because now we can go second calculate, and instead of actually doing like putting it into our equation, we can say, okay, what is it going to be at 1987? 348.84. So we can predict at 1987 it was 348.84, which we didn't see, that was an odd year, and we only did this in even years. We didn't have a piece of data for 1987. You see that? So we're predicting what was happening before. We were interpolating, I guess that's the formal word for it. And now we can, what it's called, extrapolate and say, okay, based on something that we didn't even have coverage for, 2012, what's going to happen in the future? I know it's not the future now, but what's going to happen in the future? What's going to happen beyond our data set? Well, to do that, I go second calculate, and now we're going to do value of 2020. It might give us an error. Yeah, it's going to give us an error because our calculators are a very dumb, smart object. It doesn't see 2020 on the screen. So we're just going to manipulate our window a little bit. See, the X maximum was 2015. Let's make that 2025. And now when we go to interpret our data, it's going to find it. So we go second calculate, and now we go 2020. Oh, oops. Don't do that. Second calculate value, and now when we go to 2020, it's going to find it. It's going to say, okay, at 2020, the CO2, I wonder if we can look this up. I wonder if that's actually predicted to be true. 405.36 parts per million. So the last question is, okay, when is it going to exceed 420 parts per million? Well, to find that, what we're going to do is go into our y equals and say, okay, at 420 parts per million, when our y is 420, what's going to be our x value? You gotta have to like play around with your window a little bit. See, it's above here, so I just need to go zoom. Oh no, let's just change our window. Let's go y maximum to be like 500. Let's go big. And hopefully it crosses nicely. Does it cross? Bummer. It doesn't cross. So we got to zoom out a little bit. Zoom 3, enter. Because again, the goal here is to try to figure out where it crosses, figure out the x value, second calculate intersection, to figure out the intersection of when it's actually going to happen. The y value is 420, the x value is 2028. So by the year 2029, it will exceed 420 parts per million. Okay. So I'll stop there for today. Today was all about linear stuff, but again, tomorrow we're going to be moving on and talking about, okay, polynomial models and power models and even trigonometric models and all of that fun stuff. All right, let me shut off the video.